Okay, so I'd like to talk a little bit about how water-rock interactions can influence both geophysical aspects of ocean world evolution as well as their habitability in terms of the bioavailability of key elements. So we know that geophysics has some influence on geochemistry in terms of setting the temperature, the pressure, the ratios of water and rock interacting. That all depends on the geophysical setting. But geochemistry can feed back on geophysics as well. If you think about the key heat sources that can power activity on an icy world, especially in the absence of tidal heating, radioactivity is a big deal. And so the radiogenic sources can get displaced because of water-rock interaction. The antifreeze compounds also matter a lot in terms of ensuring the persistence of bodies of liquid water over long geological timescales. So antifreezes like salts or volatile compounds. And of course, water-rock reactions are essential in shaping what happens to, for example, elements. Of course, the energy supply as well. But these factors both govern the habitability of these worlds. So the questions that I'd like to bring up in this talk are, when water and rock interact, what happens to key radionuclides, so specifically potassium, uranium, and thorium? And second, what happens to key elements such as carbon, nitrogen, and sulfur? Now, in doing this, I don't want this to be just theoretical, but really ground these models with observations. And specifically, I'll make an argument here that Ceres, that we talked about a little bit yesterday, which is the largest asteroid between Mars and Jupiter, is a really good anchor for our predictions of what the chemistry of ocean worlds might look like. And the reason for this is that Ceres is pretty water-rich. You would consider it potentially an ocean world if there has been liquid over long timescales. But the surface of Ceres is covered with rock. Whereas if you go further out in the solar system, the surfaces are covered with ice, and that kind of masks the products of water-rock interaction. So Ceres has been visited by the Dawn spacecraft for about 3 years now. And we have pretty exquisite information on what the surface composition is. And even though we have some information from, say, the plume of Enceladus, salts at the surface of Europa about what the chemistries might be like, Ceres provides pretty unique information as to what the composition of the rock end member is. Now, even before Dawn got there, we knew that the surface of Ceres was the result of products of water-rock interaction. But really, exploration by Dawn has shown that the surface composition is very homogeneous. Aside from these bright spots here that are now believed to be the remnants of fluids, either maybe dug up by impacts and or squeezed out from the interior. So these bright spots are now known to be salts, and they provide potentially a really good window into what the fluids have been reacting with these rocks and what their composition was. Okay, so specifically the composition of Ceres' average surface is given here. This is an infrared spectrum acquired with one of the Dawn instruments. And so some of these squiggles reveal that the surface is mostly made of serpentine, specifically magnesium-rich serpentine. Importantly, ammonium-based clays. So keep in mind that aspect of the fate of antifreeze and nitrogen. Carbonates, and the surface is very dark, and we don't really know what the dark component is. Could be a magnetite or iron sulfides or amorphous carbon, or maybe a combination thereof. The bright spot compositions are much richer in carbon and nitrogen compounds, which is pretty exciting if you think about bioavailability of elements in liquid, as well as so the anions are usually carbonate and chlorine mostly, and the cation sodium and ammonium. Okay, so given these observations, what can we learn about the nature of the water-rock interaction and the physical chemical conditions? So who's familiar with this kind of diagram in the audience? Raise your hand. Okay, so maybe half of you. I'm sorry, so for the other half, this is what it means. So this diagram shows redox scale essentially on the y-axis. The amount of hydrogen, the F stands for fugacity, forget about that, as a function of temperature on the x-axis. And let's look at the bottom line first here, which is a border between fields where here hematite predominates and magnetite predominates on the top. So if you look at this reaction here, this is magnetite, this is hematite, and the line represents the equilibrium between the two. So you can see that H2 appears here on the right of this equation for this redox reaction. And so the more hydrogen is in the system, for example, and the more the reaction would shift to the left, you can see this on the chart here, the more hydrogen, the more you're in the field of predominance of magnetite. So this provides context for geochemists to understand what kinds of minerals would you expect at specific conditions. You can draw a line here between iron olivine or phyllite and magnetite. And so I'll plot more lines superimposed on this contextual information. All right, so let's look at the fate of carbon first. This is what you would expect the carbon species, carbon solutes to partition at given conditions. So again, the more reduced your system is, the more you tend to have reduced carbon species. So methane is at the top, oxidized carbon at the bottom. The lines are a little bit different if you consider equilibrium between solid species. So for example, amorphous carbon at the top here, and then magnesite, which is a magnesium carbonate at the bottom. You can do the same thing for nitrogen species. Again, the species with more H's are here toward the top, and oxidized form at the bottom. But now, if we go back to this information that series provides us, the actual position of the line starts to matter quite a bit. So on series, we see evidence for oxidized carbon, ammonium, and perhaps a magnetite on the surface, and so that defines a pretty narrow wedge of conditions. Actually, we can tell that hey, the redox was probably somewhere around here, depending on the temperature at which the interaction took place, well, perhaps things were a little bit more reduced if we consider some more reduced amorphous carbon, but on the whole, we're starting to get to pinpoint what the conditions were. Now, where that becomes very powerful is that we can start to predict what species would be there without being able to observe them. That's the case, for example, for sulfur species, where these conditions plot pretty firmly into the field of reduced sulfur. Now, throughout the past couple of days, we've talked a little bit about the possibility of having sulfates in fluids in ocean worlds. And so that suggests that at least in the case of series, but it seems that the conditions, for example, inside Enceladus and Europa might be pretty similar, and I'll go to this in a moment, would preclude sulfate, right? So at equilibrium, you would expect reduced sulfur species to be there. That's even more true if you consider sulfides in minerals as opposed to in solutes. Okay, so all these diagrams that I've shown you have started to become pretty complex, but it's still a very simple system compared to nature, right? You have just a few solutes, a few minerals. And so what I've sought to do with Steve Dish and Angelique Castillo, who are co-authors on this talk, is to figure out with starting compositions for plausible rock and ice, what might you get at equilibrium, and does that match what we're seeing? There are many caveats associated with this. First of all, we have to assume a rock composition that ocean worlds form with. We have no clue what that is. But chondrites are the examples of meteorites that are pretty primitive from our solar system, and they're basically our best bet so far for our starting composition. And Tom just went into how reactions might depend on the proportions of olivine and pyroxene, and so we're pretty obsessed with nailing reasonable compositions based on elemental and mineral abundances. Same thing, we don't really know what kinds of ices these worlds started with, but comet-like ices in terms of the impurities present in the pure water ice are again a plausible bet. We've also tried simulations with just pure water to see what happens. And so to do these simulations, I've used this software called FreakC, stands for pH Redox Equilibrium, It's freely available, distributed by USGS, and it does all the bookkeeping, because we can keep plotting all these diagrams for hundreds of species, and that's been done numerically. Now, the quality of the simulation hinges on the quality of the thermodynamic data that go into it. And so feel free to talk to me after the talk if you're interested, but we spend quite a bit of time trying to strike the best compromise possible between having a comprehensive set of data that's still as internally consistent as possible, so that the simulations make as much sense as possible. And what that allows us to do is simulations at a variety of conditions, temperatures and pressures and ratios of water and rock. Now the code that I use to make those simulations, kind of a parallel version of Freaksy, is freely available online. All the input files that are out there too, so you can play around if you're interested, and modify those starting conditions. If you're not a modeler, you can also use the output files that are available as supplementary material to the paper that has all these results. And so take the exact concentrations and mineral abundances and so on. Okay, so here's a typical result from one of these simulations, and this shown as this pie chart here, which shows the mass fraction of the whole mineral assemblage that's made of a given mineral. So we're looking at rock mineral assemblages at equilibrium, resulting from the interaction of this carbonaceous chondrite with a comet fluid at a 1-to-1 mass ratio. And the conditions here are about 1,000 bars, 100 megapascals, and 0 degrees Celsius. So what you're seeing here is mostly serpentine makes up half of the assemblage, with some magnetite, some ammonium-based clays. The nitrogen here comes partly from insoluble organics in the chondrite, and partly from the comet fluid. The results change a little bit with temperature and pressure, but comparing this again with series, given the caveats that we have. So A, we don't know if chondrites are a good representation of the starting rock. B, we don't know if the simulations go all the way, or if the reactions go all the way to equilibrium. As Tom mentioned, especially at low temperature, things might take maybe up to millions or billions of years to go to completion. And C, there are some caveats as to the quality of the data that we put into the models. And yet, qualitatively, the parallel is pretty striking. It seems to suggest that water-rock interaction in these ocean worlds, and Ceres being just an example, that's actually kind of a cold end member of what might happen, no tidal heating, seems to show that interaction has proceeded long enough that these reactions go to equilibrium. And so we can use these simulations to predict what happens to carbon and nitrogen, sulfur, etc. So this is just one starting mix, but we can play around with different starting assemblages, different water-to-rock ratios, and here's how the results change. So there are some subtle differences. We can also look at what happens to the fluid in equilibrium with that rock. And here I've put this side by side with what's seen at the bright spots on Ceres. And you can see we're seeing some reduced nitrogen, a little bit of wedge of oxidized carbon, some sodium and chlorine. So at least from an elemental composition standpoint, we have a pretty nice parallel. Again, this, you don't want to equate this to this because even if fluids are squeezed up to the surface, some chemical fractionation can happen upon freezing due to space weathering once on the surface, etc. Here's how the conditions vary. Okay, so just a quick conclusion about what we've learned about the fate of carbon. Kind of spans oxidation states from oxidized to reduced. There may be some kinetic limitations, preventing full reduction to methane. And so there may be metastable organic compounds on the way. Nitrogen tends to end up more reduced. Now we're seeing ammonia in the plume of Enceladus as well, but there's probably some nitrogen as well there. So it could be that escape over time of hydrogen through the plume that's been seen as well tends to oxidize the interior. And sulfur should be mostly reduced, unlike what we're seeing on the surface of Europa. So that would seem to suggest that any oxidized sulfur is the product of exogenic inputs, either from IO and or from radiative processing. Okay, so quickly toward the end, I'd like to talk a little bit about the influence on geophysics and the fate of radionuclides and antifreezes. So these pie charts here now show the partitioning of potassium from one of these simulations. So exactly the same simulations I just showed earlier, except we're just looking at potassium now. Potassium starts out in dry minerals, so if nothing happened to it, every pie chart would be completely yellow, and you don't see that at all. The fate of potassium here is either to remain in rock as it gets hydrated, okay, or to get leached into fluid, and that happens here at low temperature, and that's the gray pie charts. So what happens there? Actually, I'll show you next with what happens to the antifreezes. Specifically, I'll focus on ammonia for the sake of time. So ammonia is a very potent antifreeze, depressing the melting point of a water-ammonia mixture from 273 when there is no ammonia down to 175 Kelvin or so if there's 30% ammonia in the mix. These pie charts show the fate of nitrogen under different conditions. And you're seeing that, ignoring these two yellow ones here, essentially, ammonia stays where it is at higher temperature, but it turns nitrogen goes into making ammonium minerals at low temperature. And so what happens there is that the potassium that's in minerals gets leached into the fluid at low temperature and substituted for by ammonia that gets protonated into making ammonium and incorporated in the rock. And going back to series, we see a lot of these ammonium minerals on the surface, which suggests low temperature water-rock interaction where the substitution happened. And the feedbacks on geophysics are pretty impressive potentially, because we're leaching a key radiogenic heat source into the fluid and depleting an antifreeze over time, right? Ammonium minerals remove the antifreeze effects of ammonia. So just to conclude on the fate of radionuclides and antifreezes, potassium can be leached at low temperature. Uranium and thorium tend to be very insoluble unless the fluids are very oxidized. So you might see this at the Earth's surface, but the more reducing conditions inside ocean worlds, you would expect them to not be leached at all. Ammonia tends to be conserved in fluids, which is kind of good news if you want to have oceans persist over time, unless water-rock interaction happens at pretty low temperature and proceeds to completion. So thank you very much.
We have time for some questions.
Hey, Marc. So I was wondering, so when did these water-rock interactions occur? Was there a time in the early formation of this thing when temperatures were warm enough that it was mostly liquid water around, and that later froze? Is that?
Are you talking about specifically
like
smaller asteroids?
Well, in like the series, was there a time when the temperature of the place was warm enough that there was liquid water in these surface environments, or?
I think it really depends on the size of the object. So if you're talking about, say, small asteroids in the solar system, these will cool very quickly. And so to get any sort of melting in the first place, you might need very early interaction. That might not necessarily last long enough to get this to happen. In the case of Ceres, as we saw yesterday, it seems increasingly likely that Ceres has had very prolonged, low temperature, sluggish interaction over time, in which case that scenario is more likely. And then moving to moons, it seems to me, at least for small moons, say Enceladus, that essentially hinges on the magnitude of tidal dissipation and heating. And so all bets are off as to how recent that is, whether it's been continuous or discrete and periodic, say, and what temperatures are able to be generated, hot or cold.
I have a quick question. is the there's going to be like latitudinal variations in temperature as you go to the pole.
Yeah.
Are there any sort of long-term consequences of that differential in temperature due, because you saw if you know the temperature variations produce some sort of substantially different reactions. So are there long-term chemical reactions consequences of that?
It's hard to say. So the hotter the conditions, the faster the reaction, and so it's hard to tell if you know the imprint on the chemistry is say your peak temperature at which most of the reaction happens very quickly, right? And then as you cool, there are not many modifications because the kinetics are just going to be slow enough, and then you freeze, you know, and so you kind of freeze the hot the output of the hot chemistry in place, or if you're able to maintain cold conditions so that you have an overprinting of the cold chemistry happening. Given the observational evidence that we have, so the plume of Enceladus is kind of one data point, right? But Ceres, the surface in terms of composition is extremely homogeneous, which suggests that when the surface was in place, you know, it was the result of very pervasive fluids moving around all over the place, and so there wasn't really latitudinal, you know, stratification of the chemistry. But that's just the observations we have. Yeah.
Marc, these ammoniated phyllosilicates have had me kind of confused for a while for a number of different reasons. But where, if anywhere, do we see them on Earth, and what kind of environments?
Yeah, so on Earth we see them in biased environments in the sense that mostly in sites where you have organic matter decaying, and so the nitrogen in those phyllosilicates that is forming, so ammonium illite or montmorillonite and so on, tends to come from living matter that's been decaying, and there's not much data out there for abiotic formation of these clays, and specifically we don't actually know, I think, from experiments if the exchange between ammonium and potassium at low temperature happens, or at least on what temp scales it happens. The papers I've read regarding the biological input of ammonium into the clays suggest that the exchange is rapid, so that it's not kinetically limited even at low temperature. But we don't really have any clue from systematic experiments at different temperatures and other conditions that of how systematic that exchange can be. Yeah.